Let me first just review the position and velocity and acceleration sketches from class on the first day. The first problem was we had an elevator, and let's say the elevator is on the ground floor, and you get in, and you push the button, and you say, I want to go up. And the elevator goes do-do-do-do-do-do-do-do-do-do, and then it stops at the upper floor. And then maybe people get out and come back in, and then you push the button for the lower floor, and it goes do-do-do-do-do-do-do-do-do-do, and stops there. So I wanted to draw a graph of position versus time, and then we can try to get the velocity versus time and maybe even the acceleration versus time. So let's start. Our position is going to be y, because we typically use the variable y for a vertical coordinate, and then it's going to be a function of time. Let's just say that y equals 0 is the ground floor, and so we dwell at the ground floor for a little while, and then the elevator starts to go up. And I don't know exactly what happens right at this instant, but then after the elevator goes from not moving to moving upward, then I think it's pretty typical. You could feel in your gut the elevator accelerates upward for a short time, but then it reaches constant velocity. So most of your elevator ride is going to be at constant velocity like this, nice straight line, and then it slows down, and then it kind of dwells at the upper floor for a while people get out and people get back in, and then the doors close and it heads back down, and there's a little period where it kind of speeds up, but then it's basically going down at constant velocity, and then finally you reach the ground floor again. So I think that position versus time looks something like this. So this is the upper floor, and this y equals 0 represents the lower floor. So that's the position versus time. And then we can say, well, what does the velocity versus time look like? Well, I can draw another graph down below that. So it's the same time axis, but now this is the y coordinate of velocity, which is the same thing as the rate of change of the vertical position with respect to time. So it's dy by dt. And I think now we need to be able to go either positive or negative. And I also made this too big, but we'll just live with that. I think what we're going to see here is initially we're not moving here, so the velocity is 0. And now the doors close and it starts to move up, so the velocity, so maybe we don't know what's happening in this little rounded part, but it seems like the velocity is positive. And then we get close to the upper floor, so it has to slow down. So then it seems like I want to draw not quite vertical line, but a pretty close to vertical line here connecting this piece to this piece. Then so this feature is kind of right below this feature, and then I want to draw an almost but not quite vertical line here. So then this feature is kind of connected to this feature. Okay, now we're not moving again, so that's 0 velocity, and then the elevator goes downwards, so that's a negative velocity. I think we're going to see something that looks just like this but reflected about this vertical axis. So whatever that distance is, it's going to be a similar distance down here, and then it's going to look, oops, well, that was supposed to be a straight line, and then this is supposed to be a straight line. So then this, now we're not moving over here after the elevator has stopped back on the lower floor. So then this little feature, let's see, so this region, this is like maximum downward speed, and this is our maximum upward speed. Maximum downward speed corresponds to this straight line portion here of the position versus time. Maximum upward speed corresponds to this straight line position here. And then see, there's a tiny little curvy part where the elevator is speeding up or slowing down, or it's speeding up or slowing down. And that's this part where the velocity is changing. So maybe it doesn't change totally abruptly because that would be very uncomfortable. So it's changing with some kind of maximum acceleration. And then finally, we have to find a place to draw it. I didn't plan very well for that, but we should draw some kind of an acceleration versus time graph. Maybe I'll just stick it up here. Here is the vertical acceleration, which is the rate of change of the vertical velocity, and then that's going to be versus time. What is that going to look like? So we want to take the velocity graph and say, what is its change? So here the velocity is not changing. Here the velocity is not. So the velocity is only changing while there's a non-zero slope of this. Right, the acceleration is only non-zero while there's a non-zero slope here. So here the elevator accelerates upward, so there's no acceleration here. And then when we get to this point, which is the curvy part here, now there's an upward acceleration that lasts a short time, and then the elevator is not accelerating. And then we reach the point where the elevator wants to slow down as it approaches the upper floor. So there's a negative acceleration for a short time here, and then there's no acceleration because the velocity is 0, it stays 0. And now it wants to go from not moving to moving downwards, so that's a negative acceleration. So there's a negative acceleration here for a short time. And then we get to the point where we're moving down and we're approaching the lower floor. So then to slow down, when we get to the lower floor, there's going to be an upward acceleration because the velocity goes from being negative to being 0. Here the velocity is 0. Here the velocity is going from 0 to positive, so that's a positive change in the velocity, so that's an upward segment of acceleration. Here we're moving at constant velocity, so the acceleration is 0. Then as we approach the upper floor, we have to go from moving upward to not moving, so that's a negative change in velocity. That's a negative acceleration. So that's this little downward blip here. And then the elevator stays at 0 velocity while people get in and out on the upper floor. And now we want to move back down toward the lower floor, so we have negative velocity. We want to go from 0 velocity to negative velocity, so that's a negative change in velocity, so that's an acceleration downward. And then we go downward at constant velocity, and then we go from negative velocity to 0 velocity, so that's actually an upward change in velocity, right? Because you're going from negative to 0, so that's an upward change. So that's this little blip upward, which corresponds to, here's a positive slope, a negative slope, a negative slope, a positive slope of this velocity versus time curve. So that was the first of the two graphs that I wanted you to discuss. Again, it was just kind of a warm-up exercise, and I didn't give you any background information, so you would just have to draw on your group's collective memory of your earlier physics course. So now let me do the same thing for the case of the basketball. In Wednesday's class, one of our examples was, let's take a basketball, and let's say I hold it at a height of about 2 meters, and then drop it, and I'll let it bounce twice, and then I'll catch it. So let's just do that so we have the real video that we can then make a graph of. Do it again. So I let go of the basketball, and it fell under Earth's gravitational force, and it bounced. And remember, after it bounced, it didn't make it up to quite the height I dropped it from, because in the bounce it lost some energy. Then I didn't touch it. It bounced again, and it came back up again, not quite to as high as it did on the first bounce, and then I caught it. So let's look at the vertical position. I think I'm going to try to make one big set of axes and draw everything on one big set of axes this time. So here is time, and we're going to start out, this will be the vertical coordinate, y. There's y versus t. We started out some height above the ground. I held it above my head. Let's say that's 2 meters. So we didn't really put numbers on the graph. Let's say that's 2 meters. So I'm holding the ball up here at y equals 2 meters. And I'm holding it for a while, so it stays that way for a little bit. And then I let go. This is something you probably would have had to puzzle over with your group mates. So I think the best way to understand this is when we actually draw the velocity graph. It's going to turn out that this is an arc of a parabola. The ball, initially, I just let go of it, and it starts out with 0 speed, and the speed gets bigger and bigger and bigger and bigger, and the speed is maximum just before it hits the ground. That corresponds to the slope of this graph. So the slope starts out 0, and the slope gets bigger and bigger and bigger and bigger and bigger until it hits the ground. And then the ball bounces, and after it comes back up, it's basically going to retrace the same motion. If the collision with the ground lost no energy, if it were a 100% elastic collision with the ground, then this would just be a mirror image. But it actually lost some energy in the bounce. You can tell it didn't go up quite as high. So it's not quite going to be a mirror image. It'll be kind of a shrunken mirror image. It's just going to go back up like this, but to a lower height. This is the instant, so you can see when the slope becomes 0, that's the instant when it's at the apex of its orbit, and then it's going to go back down like this, and then it's going to bounce up again, and again it'll reach not quite as large a height, and then this is where I caught it. So then I catch it here. So I release it here. Here's the first bounce, here's the second bounce, I catch it. It's really important that this height is lower than the original height because that was what we saw. There's some loss in height between the top of its motion when it first bounces and when I first released it, and there's some loss in height between the top of its motion after the second bounce and when I released it. Then we can try to look at the velocity, the vertical velocity versus time. Call that v sub y. So I'll draw that in this orange color. The vertical velocity here is 0. Then you see the slope of this thing, it starts out 0 and it gets negative and it's more and more and more and more negative. So this is actually sloping down. So it starts out 0, but it's negative and it gets more and more negative. So it's kind of like that. And it's most negative. So the velocity is the largest downward just before it bounces. And then after it bounces, if it bounced with no loss of energy, its speed, the speed is the absolute value of the velocity, the magnitude. If it bounced without losing any energy, the speed immediately after would just be the opposite. It would be this same magnitude, but on the upper side of the axis. But it actually bounced with a little bit less, it lost some energy, so it actually has an upward velocity which is a little bit smaller than the downward velocity just before it bounced, so it's something like that. This slope, by the way, is minus g, where by g I mean 9.8 meters per second, or in old-fashioned units, 32 feet per second. That same slope is going to be the slope here, because that just represents the fact that the only force acting on the basketball is gravity, or ignoring air resistance. So I want to draw that same slope, we're going to go down with that same slope. See, it crosses through 0 here. That makes sense because this is where it's highest in the air, and at the point where it's highest in the air, it's momentarily at 0 velocity, just for an instant, and now it keeps going down like that. So that makes sense. See, here it has an upward velocity, which is big, and it's a smaller and smaller and smaller upward velocity. At this instant, it has 0 velocity, and then it's negative velocity, and it's a bigger and bigger and bigger negative velocity. Now it bounces again, and we want to make sure that this goes up a little bit less than that to represent that sort of loss in energy. I think I exaggerated this difference in velocities, and I'm exaggerating it here even more. I'll explain that in a second. This is beyond, like, you don't have to be that subtle. In fact, you didn't even have to get to this second problem. I just wanted to make sure you had some way to practice working in groups. Then we did something like this, and then I catch it, so now the velocity is 0. So again, here the slope is minus g, and here this slope is minus g, because these are the periods when it's entirely under the influence of gravity, nothing else. See, there's a big positive slope here, which is the elastic force. This is when the basketball is compressing and then decompressing. So then if we draw the vertical acceleration so this vertical velocity, again, was dy by dt, and this vertical acceleration was the velocity y by dt. The slope here is 0, and so it's basically the slope of this curve. So this is fine, it's just like that. We have something that's minus g. I'm going to make minus g be kind of small here because that's fine. And see, over here, the slope is also minus g. And over here, the slope is also minus g. And then the slope is 0. Of the orange curve, because the purple curve is the slope of the orange curve. Now the thing is, notice that we pretty abruptly go from a negative velocity to a positive velocity, so in order to do that, for a short time, you need a very big positive acceleration. If you were an ant riding on the basketball, you would find that instant when the ball bounces quite uncomfortable, as if you were in a pretty rough amusement park ride. Here the slope is minus g, so the acceleration is minus g. Here the acceleration is some much bigger than g in magnitude, positive number. Here it's, again, negative g, and here it's, again, this much bigger than g positive number, and here it's minus g. I think that makes sense. This might be, should this be just as big as this, or should it be a little smaller? I actually don't know whether it should be about the same or a little smaller. I'd have to think about it, so I'm not going to think about it here while you watch. Another thing is, you don't have to remember this, but if you remember, at this point, the energy is all kinetic. So it's of the form 1/2 mv squared, and here, by the time we get back to here, the energy is all potential, so it's of this form mgh, where h is just the biggest value of the altitude. Notice that when we bounce, so when the ball bounces, the velocity, the speed, the magnitude of the velocity just after the bounce is smaller than the magnitude just before the bounce. And then here you see this height at the end of well after the first bounce is smaller than this height before we release it, and this height is even smaller. But this is just 1 power of h, and this is 2 powers of v. If this height gets smaller by like 20%, and let's say this height gets smaller by like 20%, then roughly, so if you have like 0.9 squared is about 0.8, if you lose 10% and you square that, that's like losing 20% approximately. So I actually think that if this is like a 20% drop and this is like a 20% drop, then this should have only been like a 10% drop in speed, because you square this. Just after the bounce, there's some speed. That's squared. And then that all turns into, you see this mgh, gravitational potential energy. One thing I did not quite right when I drew this bouncing is I made this ratio of speed after the bounce to speed before the bounce more dramatic than this ratio of height after the bounce to height before the release. And it should have been the other way around. So if this is like, let's say this is 1.0 and this is 0.8 and this is 0.6, then I think this should have been like 90% as big as this, and this should have been like 90% as big as this. So that's one way that when I just went through and drew this kind of off the cuff, I didn't do quite as good a job as I could have. Still, this was mostly just to kind of get your physics brain cells working again, because I know it's been at least a year since you did physics before, and for many people it's been longer than that. So now let's move ahead and talk about forces. Here, by way of review, is a problem we like to talk about in Physics 8. I pull on a cart. The cart moves. I don't move. Why don't I move? I pull on the cart. The cart moves. I don't move. Why is that? And I guess the obvious answer is the cart is on wheels. I'm wearing sneakers. To put that into physics terms, there is a frictional force between my feet and the floor, because my sneakers give me good traction on the floor. But there is no such frictional force for the cart, because the cart is on good wheels. So let's see if we make things more equal. Let's put me on wheels too. Now I pull on a cart. We both move toward each other. Let's try that again. I pull on the cart, and we both move toward each other. This cart is pretty massive. I think that explains why I accelerate more than the cart does. Try one more time. I pull on the cart. So of course the cart is pulling back on me by Newton's third law. And since now neither of us has any significant friction with the floor, we accelerate toward each other. Good. But if I have a good frictional contact with the floor, then okay, the cart moves toward me, but I don't move toward the cart because the frictional force exerted by the floor on my sneakers offsets the force exerted by the cart on me through the rope. Good. So you just saw the video of me pulling the cart, and there were two versions. In one version, I'm standing on the ground wearing sneakers. In the other version, I'm standing on a kind of skateboard that eliminates the friction between me and the ground. Let's first talk about the version where there's no friction. First, I'll just draw a little picture of the scenario. Here is the cart and it's on wheels. And then there's me, except that I'm on wheels. The rope is basically just a mechanism of communicating the force between me and the cart. So there's the rope. So even though I pull the rope and the rope pulls the cart, it's really good enough to say that I pull the cart and the cart pulls me. The rope won't really be a character. The rope is just transmitting that force. And we're both on the floor. So now I can draw two free body diagrams. I can draw a free body diagram for the cart and I can draw a free body diagram for me. So let me first draw a free body diagram for the cart. I always draw a little plus sign, like kind of a cross to indicate the center of mass of the object of interest. That's supposed to represent the cart. And if we want to do forces in both directions, there's actually a downward force. This is a gravitational force exerted by Earth on the cart. By Earth, that's the cart. I'm going to call the cart C, and then me is going to be M, and E is the Earth. Then there's actually, F is the floor. E is Earth, and F is the floor. Then we have a contact force. Also, by the way, the magnitude of this force, you might remember, is mg, where M is M of the cart, mass of the cart times G. And then we have a normal force, or a contact force. I'll call it the normal force. And this is by the floor on the cart. And because the cart is not accelerating vertically, this is also going to equal mg. It has to, m cart g. You know, the cart's not going up or down. It's not accelerating up or down. And you know there's this gravitational force here. So what keeps the cart from accelerating vertically must be that there's this normal force balancing it. Then I'm pulling on the rope. So now there's a force in this direction. This is the contact force, or it's also the same as the tension in the rope, but that's kind of a detail you don't have to remember right now. So this is exerted by me on the cart. And that's just whatever force I'm pulling with. I want to draw the same diagram for me. So that's supposed to represent my center of mass. I'm drawing it the same color as me. Now it appeared that the cart's pretty massive. I think it was more massive than I was, because I remember when I pulled on the cart, I moved toward it more than it moved toward me. So I think, I didn't try weighing it, but I think that cart probably weighed about twice as much as I do. Therefore, I'm going to make this line. This is going to be the gravitational force by Earth on me, and that equals my mass times G, M for me. Then there's an upward force, which is the floor on me, and these are the same. Of course, it's different from this, but it's the same. I'm not accelerating upward or downward. So the normal force, this is the normal force by the floor on me, and that also equals my mass times G. These two forces balance. I'm not accelerating up or down. These two forces balance. The cart is not accelerating up or down. The purple lines are bigger than the green lines because the cart, I think, is more massive than I am, let's say by about a factor of 2. But this is where Newton's third law comes in. You say, how big should I make? So you know that if I'm pulling on the cart, then the cart is also pulling on me. So how big do I make this line? And you might say, well, gee, all of the green lines are smaller than the purple lines. Maybe I should make it smaller. But no, Newton's third law says that if I am pulling on the cart with a force of a given magnitude, then the cart is pulling back on me with a force of that exact same magnitude in the other direction. So this line pointing from me toward the cart has to be the same length as this line pointing from the cart toward me. So this is the contact force of the cart on me. So the force exerted by me on the cart is the same magnitude as the force exerted by the cart on me, but they point in opposite directions. In this diagram, I'm pulling the cart that way, to the right, and in this diagram, the cart is pulling me to the left. So I move toward the cart moves toward me. You can see vertically that the cart doesn't accelerate vertically. You can see vertically that I don't accelerate vertically. But if you look at the horizontal forces, I'm going to accelerate that way, and the cart is going to accelerate that way. Also notice, in the free body diagram, this is the free body diagram for the cart. In the free body diagram for the cart, you only include forces acting on the cart. In the free body diagram for me, you only include forces acting on me. So notice this is floor on the cart, me on the cart, earth on the cart. This is the floor on me, the cart on me, earth on me. So everything in a cart's diagram is on the cart. Everything in my diagram is on me. And the place where Newton's third law comes in is it allows you to say that these two lines have to be the same length and they point in opposite directions, because the force by me on the cart and the force by the cart on me are an interaction pair, we say. So by Newton's third law, the force by me on the cart is the same size as the force by the cart on me, but in the opposite direction. So now I'm going to accelerate toward the cart. The cart's going to accelerate toward me. So we can use Newton's second law. And Newton's second law, so Newton's third law allows us to relate these two arrows to each other. Newton's second law says that the acceleration, and we're going to say in the x direction, because typically we say this is the x direction and this is the y direction. The acceleration in the x direction of the cart is this force, the contact force of me on the cart, divided by the mass of the cart. And then the acceleration in the x direction of me is the force, the contact force. The C means contact, it also means cart here. Maybe I should have chosen a different letter. This is the force by the cart on me divided by the mass of me. Well, again, I use m for mass, I also use m for me. So these two numerators are the same size, but the denominators are different sizes. Let's say that I moved, oh, by the way, I moved to the left, the cart's moving to the right. So this seems to be, let's say this is minus 2 meters per second squared. Then let's say this turned out to be plus 1 meter per second squared. This is assuming the mass of the cart is 2 times the mass of me. So if the mass of the cart is twice my mass, then if I accelerate toward the cart with, say, 2 meters per second squared, the cart's going to accelerate toward me with 1 meter per second squared. So it's the same force, although when the cart sees a force pointing to the right, I see a force pointing to the left, but it's the same magnitude force, but because the cart is more massive than I am, I accelerate toward it more rapidly than it accelerates toward me. You don't have to do too much of that in Physics 9. It's really the focus of Physics 8, but it's sort of expected that you've seen it before, so that if it's used in an explanation, then it's not totally unfamiliar. We draw a picture of the scenario. We think about what the forces are. We draw a free body diagram, one diagram per relevant object. We enumerate all the forces on each relevant object, and the diagram helps us to do that. Sometimes we use this concept of equilibrium, that the acceleration is 0, to say that these arrows have to be the same as each other, these arrows have to be the same as each other. Sometimes we use the third law to say these two forces are just different sides of the same coin, so they have to be the same magnitude and point in opposite directions. And then we go over and we say, okay, now we're going to add up all the forces in the x direction, and there's only one force in the x direction acting on me, there's only one force in the x direction acting on the cart, and we're going to take all those forces, there's only one of them in this case, divide by the mass, and you get the acceleration. Or in this case, there's one force acting on me in the horizontal direction, divide by my mass, you get my acceleration. That's how we use Newton's third law and second law together. And again, the first law really doesn't tell you anything very often. It really is just a reminder that all of this stuff only works properly when you're using it from the perspective of an inertial reference frame. In other words, a frame which is not accelerating, a frame which is not rotating. Now let's edit this picture for the case where I am wearing my sneakers on the floor. There's no skateboard underneath me. So if there's no skateboard underneath me, I'm going to erase. So then I'm like anchored to the floor there. And then if my sneakers have good friction, so I'm pulling on the cart's pulling on me, the cart is accelerating toward me, I'm not going to accelerate toward the cart. The reason I'm not going to accelerate toward the cart is because, and this is another arrow, the arrow is pointing that way, and it's the same length as these other two arrows. So this arrow, and this arrow are all the same length. And this is a frictional force of the floor on me. I know the subscripts are a little tricky here, and the letters might be a little small. Let me try to read it out loud. So we've added to this picture the frictional force. That's what this F is. In fact, I mean, sometimes we say S for static friction, so you can say F for frictional or S for static friction. It doesn't really matter what letter you use there. But it's on me. It's on my diagram, so it better be a force acting on me, and it's by the floor. So the floor is pushing up on me, and the floor is also preventing me from moving toward the cart. So that's the normal force, the floor pushing up on me. And there's also the frictional force, the floor preventing me from slipping. Now if you say, what am I doing? You see, this force is still there, but then there's minus this frictional force of the floor on me. And these are the same size, but they point in opposite directions, so they cancel each other out. So now this is going to be 0 meters per second squared. I'm not going to accelerate, but notice we didn't add anything to the diagram for the cart. So the cart is still going to accelerate toward me, but now I'm not going to accelerate toward the cart because the frictional force exerted by the floor on me is offset getting the contact force, like transmitted through the rope, of the cart on me. I pull on the cart, that's this arrow. By Newton's third law, the cart pulls back on me, that's this arrow. These are the same size. And then because the static friction exerted by the floor on me will try, unless I slip. If it's like too big a force is needed, eventually I'll slip, because friction eventually gives out. But as long as friction isn't going to give out, that depends on how good my sneakers are. So like if I'm on a kind of slippery surface, friction will give out sooner. If I have like really good soccer cleats, football cleats, my friction will not give out so soon. Anyway, assuming that friction holds up, and you didn't see friction give way, so it did hold up in the movie, then this arrow will be however big it needs to be to stop me from moving. These two arrows are the same. They cancel each other out. This force is the same size as this force. The net force on me vertically is 0, and the net force on me horizontally is 0. But the net force on the cart horizontally is in the direction toward me. So that's how you see the cart accelerate toward me, but I stay put. And again, in Physics 8, we would go through this again and again, and you would really understand it perfectly. In Physics 9, we just don't want it to be totally unfamiliar, because sometimes using forces is part of the explanation of how the Physics 9 topics work. We could even do something simpler that involves just me. Here I am, I walk forward. That seems pretty easy. But then imagine that you're on a sheet of ice. Here I am, I walk forward. Oh, because to push myself forward, I need the floor to push me forward. This is like yanking the tablecloth out from underneath all the stuff on the table. So we're going to go 1, 2, 3. Amazing! So in that last video clip, you saw Mary. Let's put Mary over here. And Mary was on roller skates. And then you saw a little cart underneath Mary, and it was also on wheels. And then you saw me over here, and I'm going to make my arm really long like that. So then you saw me I was pulling on a rope. Then I am anchored to the floor because I'm wearing good sneakers. But Mary's wearing roller skates, and underneath Mary is another little skateboard-like thing. So then I yank on the rope. And what did you see? You saw that the little board thing on rollers, the little cart underneath Mary, came rolling out from under her, but Mary didn't move at all. She moved downward by the 10 centimeters between what she was standing on before and the floor, but horizontally, she basically didn't move at all. And you could say, well, how do we explain that? And if you draw a free body diagram for Mary, here's Mary, and this is a free body diagram for Mary, and there's Mary's weight, so that's a force gravitational by Earth on Mary, which equals her mass times g. And then there was a normal force exerted by whatever that orange thing is. I'm just going to call it the orange thing. By the orange thing on Mary, and these are the same size. And then there's no other force on Mary. See, there's no frictional force between Mary and the orange thing because they're connected by wheels. And then meanwhile, we could draw a free body diagram for this thing. I guess we could do it. I didn't intend to do it, but we could do it. Here's the orange thing. So the orange thing has its own weight, and it I think seems like it's probably like a quarter of Mary's weight. So this is the gravitational force by Earth on the orange thing, which I don't want to name. I don't know what to call it. Oh, now there's the contact force by Mary. See this force, there's another force the exact same size as this. Well, this is actually better than I realized. So, yeah, there's the contact force by Mary on the thing. This downward orange arrow is the same size as this upward purple arrow, because this is the orange thing pushing up on Mary, and this is Mary pushing down on the orange thing. But you know that orange arrow is the same length as this arrow is the same length as this, which is just Mary's weight. It's her mass times g. Okay, now you know the orange thing is not accelerating up and down, so we need an upward arrow, and this upward arrow equals this length plus this length. So this upward arrow has a length which is this length plus this length, and this is the normal force of the floor on the orange thing that I don't have a vocabulary word for. That's vertically. Horizontally, well, you see there's no friction because it has wheels, but there is a force pointing this way, and this is the contact force by me on the orange thing. And then you could draw a diagram for me. So here I am. Okay, what's gravity doing to me? Well, I think I weigh about 30% more than Mary does. My gravity arrow is a little bigger. This is gravitational force of Earth on me. And then you know I'm not accelerating up or down. This is the normal force of the floor on me. These are the same because I'm not accelerating up or down. Oh, let's call this number 3. 1, 2, 3. There's the contact force by me on the orange thing. So by Newton's third law, here's the contact force by the orange thing on me. And it has to be the same length. That's Newton's third law. But you saw me not accelerate, and that's because the floor has a good grip on my feet. So now there is this same length. This is the frictional force, which you could call static kinetic friction, S, I just say F for friction, of the floor on me. So all the forces on me balance. I don't accelerate. All the forces on Mary balance. She doesn't accelerate, except for that tiny little, at some point this thing disappears and she goes down to meet the floor. But horizontally, she doesn't accelerate. But the orange thing, the thing we're drawing in orange, the little wheeled cart underneath Mary, does accelerate. It accelerates to the left. I think that turned out to be a better example even than I expected. I'm standing here. I have a good grip on the floor. Mary's standing here. She's completely isolated horizontally by her roller skates. Here's the cart. The cart has the rope attached to it. I'm going to pull on the rope, and the cart comes out from underneath Mary, but Mary does not accelerate, certainly not horizontally, just for a short instant vertically to reach the ground. And I don't accelerate at all. And I think that's what we saw in the video clip. So I think that's kind of cool. Here's another physics 8 problem. A school bus is driving down the street at constant velocity, and a little kid's toy matchbox car, this is hard to see. Also this big roller skate, which maybe will be easier to see. School bus is just minding its own well, it's going at constant velocity. Now all of a sudden the school bus driver jams on the brakes. And what happens? School bus is driving down the street. All of a sudden, the school bus driver jams on the brakes and whoa! And the question is, what is the most straightforward frame of reference from which to analyze that scenario? Which is the frame of reference in which Newton's laws work as you've learned them? Okay, ready? That's pretty good. Okay. Side. So here's one more example. We're going to say, here's the floor. And then resting on the floor is block A. And then resting on block A is block B. Imagine they're like a child's blocks. And then resting on block B is block C. And they're all just sitting there, not moving, not accelerating. They're in equilibrium. See, A is not accelerating, so the vector sum of forces on A must be 0. B is not accelerating, so the vector sum of forces on B must be 0. C is not accelerating, so the vector sum of forces on C must be 0. How do we figure out all the forces? Actually, this in architecture is called load tracing. So usually in load tracing, you start from the roof and you go down to the ground. So we're going to start at the top. And again, we do this again and again and again in Physics 8. We're just doing this as a quick review. So let's start with a free body diagram for C. I'm going to draw C in green. Here's block C. And what are the forces on block C? There's a downward force on block C, which is, this is the gravitational force exerted by Earth on C. And its magnitude is the mass of block C times little g. Now you know that block C is not accelerating, so there must be something to offset that, and that's the upward force, the contact force exerted by B on C, or you call it the normal force. I'm going to say contact instead of normal, but okay, so these are the same. So this is the contact force exerted by B on C, and it's the same size actually, so this actually also equals mass of C times G. So then from the fact that there are no arrows horizontally, and the two vertical arrows offset one another perfectly, they balance each other, so the acceleration of C is 0. That's kind of by design, by construction. So now, let's draw a free body diagram for B. Okay, there's B. B is in orange. We know gravity is acting, and I made this bigger, so it's probably a bigger mass. So we're going to say here is, it's a little bigger than that, here is the gravitational force, Earth, on B. So that, its magnitude of that is going to be B's mass times little g. Little g is 9.8 meters per second per second. See, you can't use, it's not so fast. You can't just draw the normal force and say they cancel, because you know if B is pushing up on C, then C must be pushing down on B. So there's this arrow, which is, so we have to draw an arrow the same length as this. So it's the same length as this. And this is the contact force by C on B. So that's just the Newton's third law complement of this force. Ah, this was a good mistake. What did I do wrong here? This is the correct size, but it points in the wrong direction. Ha! So actually, yeah, that was a nonsense. Okay, I knew I did a nonsense here. This is the contact force by C on B. It points down, not up. Right? Newton's third law says that the force exerted by C on B is the same magnitude, but the opposite direction as the force exerted by B on C. Oh, that was really good. Sometimes mistakes are helpful. So that points down, and it's the same magnitude as this, but the opposite direction. So now we want, see, these two things together have to be offset by the force exerted by A. So now we want to draw something up like that. And it's this length is the sum of these two lengths. Maybe a little too big, but anyway, this plus this is going to be this length. So this is the contact force A on B. This contact force is kind of the same thing as the normal force. Okay, now we could do the free body diagram for A. A is going to be a little more massive than B, so I need to leave enough room for that. Okay, this is going to be A. This is my gravitational force of Earth on A. You see, I made this arrow a little bigger because I'm going to say that B is a little more massive than C, and A is a little more massive than B. Now, we look at this. This is a force exerted by A on B. So there has to be another force that same size, opposite direction. Okay, so it seems like it's something like that. It's whatever. So whatever this length is, this is the contact force of B on A. Contact force exerted by B on A. Now the floor is going to exert a force on A that offsets these two things together. This is going to be a big arrow. It's going to go right through there. This is the contact force, also known as the normal force, exerted by the floor on A. We said, kind of by construction, these things are just sitting there minding their own business, so none of them are accelerating. So the length of this arrow equals the sum of the lengths of these two arrows. The length of this arrow equals the sum of the length of these two arrows. The length of this arrow equals the length of this arrow. It's easy to see that everything adds up to 0 here. Now because this is B pushing up on C, we have C pushing down on B. So these two things have to be the same length as one another. And then because we have A pushing up on B, we have B pushing down on A. And these two arrows have to be the same length as one another because they're Newton's third law complements of one another. And then this is the gravitational force, Earth on A. There's the gravitational force, Earth on B. There's the gravitational force, Earth on C. So I think that's it. Yeah, so we've added up the forces on those three things. So again, a free body diagram is a very helpful graphical way to keep track of forces, keep track of which ones should be the same size as one another, keep track of their directions. It's a really helpful bookkeeping, visual bookkeeping tool.